Welcome to Essential Problems with Crip. This last video in this series will focus on coordinate covalent bonding. This is not a common thing that you will encounter in AP chemistry, but it's important to note it so that you don't freak out if you ever encounter this, right? And so notice even the formula that I'm drawing here is a little bit weird. So what is a coordinate covalent bond? It's a type of bond that occurs between a metal and non-metal ligands that actually function, right, to have a partial bond, not a partially covalent bond with the central metal atom ion. And so the important thing that I want to note here is that you will find, perhaps on the internet, a lot of ways of approaching Lewis structures, and some techniques are really horrible. And that means that sometimes they will generalize by making coordinate covalent bonds everywhere, and really this is inappropriate. Coordinate covalent bonds can only be drawn in reference to something like this. And so what's that? So let's just draw ammonia, NH3. If we just draw NH3, right, nitrogen, 5 valence electrons plus the 3, 8. And so if you draw this structure correctly, you should come away with something like this. Okay? So that's ammonia. And of course, cobalt, right? That's a metal. What is that going to do in reference to these ammonia molecules? Well, cobalt will be in the center. And essentially what's happening is that unshared pair on each of the ammonia molecules will actually be drawn towards the cobalt, and we're going to have a partial covalent bond. This is what we're calling a coordinate covalent bond. Oops, should have drawn the nitrogen over here, and then 2, right? Like that. And what you will see is the best way to kind of represent this is not as a line, but as an arrow to the cobalt. There is a couple ways to do that, but basically you might even see dashed lines to have this kind of coordinate covalent bond. And then the whole structure itself is bracketed and given a total charge, right? And again, this is due to this type of partial bonding that's occurring around that cobalt ion. But of course, we can't give it a charge because it's forming this partial bonding. And so originally, you can envision that cobalt as having a 3+ charge, and then all of these neutral ligands coming around it and forming this this type of bonding around the cobalt ion. But then that means the whole substance as a whole has a 3+ charge. Now, this is the only time where drawing this kind of bracket and giving a total charge to the structure is okay. This is not okay if you were to take one of the polyatomic ions that we had been drawing and just kind of say, yeah, bonds and charge. No, no, no. This is the only time that it's appropriate, when you have this kind of special type of bonding between metal and these ligands, what we call ligands that are surrounding it, these kind of molecules. You can have ammonia, you can have cyanide, you can have water molecules around. So if we take something like, and by the way, this would be called hexaamine cobalt 3 ion. We can have a situation where we have, say, water molecules like around aluminum. That's going to be a common one that we'll encounter when we talk about acid bases. And so something like tetra or hexa aqua aluminum ion, right, where you could have 6 water molecules around. So if I were to draw that, you'd have aluminum and hexa aqua would result in something like that. You can also have a scenario where the ligands have a charge. So, for instance, you can have the ligands be cyanide. So, in that case, let's draw one more with this. So, let's take hexacyanido iron 2 ion. So, here, iron, having that 2 plus charge, we're going to surround it by 6 cyanide ions. So that means the whole charge of the structure will be 4 minus, because that's 2 plus, and each of those CN cyanide ions are 1 minus. If we have 6 of them and the 2 plus, we end up with a total charge of 4 minus. And drawing cyanide correctly is very important, right? If you look, 5 electrons, 5 valence electrons, plus 4, so that's 9, plus the 1, so that's 10 valence electrons. If you draw it correctly, you're going to end up with this kind of triple bond, right, with the nitrogen, 2, 4, 6, 8, 10, with the carbon having this negative charge, okay? So with that in mind, we can draw iron in the center, and you can immediately see we'd have, right, the carbon end, since it's negatively charged, being drawn to the iron, and we can go ahead and do that around it. And again, if you notice, I'm drawing it in a octahedral-like formation, and then we draw our arrows, right, and put the bracket and say 4 negative, okay? But again, this would be the only appropriate time to use this coordinate covalent bonding, only when you're working with what we call complex ions. So again, we're not going to be working with them commonly, but you should be aware of this. Till next time,